Everything else we have built, the twin, the estimators, the surrogates, the learning, exists to serve one moment, the decision. A plasma is drifting toward an edge, milliseconds are passing, and something has to choose what the coils and the heating do next. This is real-time control, and it is where intelligence meets discipline. So understand the control stack first, because the whole design rests on it. Machine learning advises, a deterministic rules engine decides, the smart, flexible, learned models propose the best move, and a fixed, auditable set of rules has the authority to accept it, temper it, or refuse it. We never invert that order. The simplest controllers react to error after it appears. A classic PID loop nudging the plasma back toward a set point whenever it strays. That is reliable and well understood, but it is always a step behind, forever correcting what already went wrong. Model-based control does better. It carries a model of the plasma and uses it to anticipate, not merely react. The sharpest form of that is model predictive control. At every cycle, it looks ahead over a short horizon, simulates where each possible action would lead, and picks the sequence of moves that best serves the goal. Then, it throws most of that plan away and does the whole thing again a moment later. Plan, act, replan, continuously. It is control that thinks a few steps ahead of the plasma instead of chasing it. For the hardest regimes, we turn to reinforcement learning. Rather than being told the rules, an agent learns a steering policy by practicing millions of times safely inside the digital twin, where a mistake breaks nothing, until it discovers control strategies a hand-tuned loop would never find. The twin is what makes that practice possible. You could never let a raw policy learn on real hardware. Modern reinforcement learning pairs two networks. An actor proposes the action. A critic judges how good that action was likely to be. Methods like PPO let the two improve together, steadily, without the training flying apart. It is how a policy gets genuinely good. The whole behavior is shaped by the reward. Define what good means. On-target performance, gentle actuators, wide margins from danger, and the agent optimizes exactly that. Reward shaping is where our engineering priorities become the machine's instincts, so we design it with great care. And here, the discipline becomes explicit. This is safe reinforcement learning. The policy operates inside hard constraints it is never permitted to cross. Normalized beta stays at or below 5. Q95 stays at or above 5. These are not preferences the model can trade away for a little more performance. They are physics limits, wired in as walls the policy is never even allowed to approach. Not every decision is a fast one. Finding the best steady operating point is a search across many knobs, and each trial takes real time on hardware, so we cannot test blindly. Bayesian optimization runs that search efficiently, building a model of the response surface as it goes and homing in on the sweet spot with remarkably few trials. It balances that search with an acquisition function, the rule that decides at each step whether to exploit the setting that looks best so far or explore somewhere uncertain that might turn out better. Explore versus exploit, chosen deliberately and mathematically rather than by luck or by hand. That balance is what keeps the search from either settling too early or wandering forever. Whatever the method, the decision has to become physical action. The optimizer's command flows out to the actuators, the magnetic coils that shape the field, the heating systems that pour in power, the fueling that sets the density, turning an abstract number into a real change in the plasma. Intelligence is only real when it moves hardware, and every one of those actuators has its own limits the controller has to respect. And all of it races a clock. From a sensor reading to an actuator moving, the entire loop must close inside a tight latency budget, every cycle without fail. In plasma control, late is the same as wrong, so the last word belongs to the failsafe. Above every learned policy and every optimizer sits a deterministic override, and it always wins. If a limit is approached or a model is unsure, the fixed safety logic takes control. No negotiation, no delay. The learned models make the machine smart. The fixed rules make it safe, and safe comes first. That is the whole philosophy in one line. Let the intelligence